So first and first, it's a 15 inches. It's a MacBook Pro A1990, A1990, and the description is that. Okay. So yeah, first and first, we want to flip it over, take out the back cover. To take out the back cover, you need a P5 to take out the back cover. So for this machine, the screwdrivers that you need a P5 for the back to take out the back cover, and inside you need a T5 and a T4. Most of the screws that you will be needing on this one, most of the screws on this ones are going to be, especially inside, are going to be T5 and T4. So pop the back cover open. Okay, it looks like somebody was here before. This is bad. This is not good. This is not good. This is not good. Somebody was here before. Yeah, some of the shields are missing. This is put wrong. I mean, this is put. This is not how it should be. This is done wrongly. The battery data cable is not present. The keyboard and trackpad shield is missing. The touch bar shield is missing. The audio shield here, the audio cable shield here is also missing. And this battery definitely was taken out before for a reason I don't know. Yeah, it says dead, and I can see signs of pre-work here, and I'm not sure exactly what. First, let's confirm the state of the logic board, but this is not good. Yeah, usually when you have and for example, look at the Wi-Fi connector cable. Say it was put wrong. Imagine the Wi-Fi connector cable is put beneath the board. The cables are supposed to come, the antenna cables are supposed to come over the board, not beneath the board. Yeah, and you have missing screw. This is missing. Nah, this is really not good. Okay, first and first, let's just check. Say if I have a short on PP bus. We don't have a short on PP bus. Okay, so we're not sure exactly what the PPDCINs have done. Let's just take out the board and just give it a comprehensive view to understand what has happened. It doesn't look good. So the first screwdriver I'm using is a T5. Afterwards, I'm just gonna take out all of the T5 screws, and then I will take a T4. And also, I'm also gonna need a T6. A T6 for. So I need a T6 here, and then I need a T6. I'm just gonna I'll show you guys shortly. I'm using a T4. And also the screws used here are wrong. Those are not supposed to be the screws to be used there. It's important that the screws are put right. It's important that the right screws goes to the right place. Yeah, so this screw that I'm getting out of here now is supposed to be for a different location completely. So definitely this machine went to yeah, whoever did this job before didn't do a good job. Didn't do a good job. So, yeah, the screws are mismatched. These are not supposed to. Most of the screws are not where they're supposed to be. And we also have missing screws. And this was definitely put together by somebody who has no idea. Definitely. I mean, this is definitely by somebody who has no. I mean, so I'm using a T6 for the heatsink, the left and right hand side of the heatsink. So I mean, whoever has basic repairs I mean, just the least basic repair, which just to put a machine together, that is the least required. That person will be able to put this machine together, but whoever did put this machine together, or whoever attempts to fix this machine, has no basic understanding of repair. So I wonder what they did, and I did also see some kind of attempt around the CPU by the CPU MOSFET. I'm not sure. I mean, this, for example, this is supposed to be up, not down. So I'm just gonna put this aside and get to see exactly what is it that they're trying to do, what they do, and then we take it from there. We're not that hopeful, especially. Okay, let's see what's happened here. Let's give it a visual inspection. So far, but looks clean. We yet to make measurements, basic voltage measurements. We yet to do that. So this was where we found flux. So we'll take out the heat sink, see what is it that, if there is a reason why they had to maybe replace the CPU MOSFET for some reason. Yeah, I'm not sure. So let's quickly take out the heatsink. I'm using a T5 screwdriver. Yeah, it's important to know your screws and know where they are placed. It's very, very important. I'm just gonna take that out, see what they did here. Okay, it doesn't seem like they replaced it. Okay. Okay. It doesn't seem like it was replaced. So okay, now let's check for basic. Let's check for short and 3 volts rails. Oh, sorry. This basically, yeah, this board, the board itself, it's a 2018 1915 inches board, A1990, and the board ID it's 820-01041-07. I'm not sure if you guys can see that. It's 820-01041-07. So what we want to do now is we want to open the board view and the schematic of that board. So come here, we want to open the board view so you guys can be able to follow along exactly what we are doing. So the board view, it's where is it? Where's the board view? So I'm basically going over some of the. Okay, if I don't find it here, I'm gonna just have to type it. Okay, I don't see it. I'm just gonna check for it. So it's 0-010 41. So there you go. 0-041. So that is the board view. Now let's open the schematic. Schematic. So it's 820-010. Okay, that is schematic. So we will be able to follow along the board view as well as the schematic. So first thing first, we want to measure. We want to check to see if we have or short. It's just random measurements. Just see if we have shorts anywhere. So measuring for shorts, we use capacitors. one side is expected to beep, the other side is expected not to beep. So if we get beeps on both sides, our multimeter has to be, put in our multimeter in continuity mode. So if we get beeps on both sides, it means we have a short. If we get beep on one side and there is no beep on the other side, which means that we have a healthy capacitor. So most of the lines that we wish to measure, there are capacitors that are connected to those lines. So it's easy for us to just measure those capacitors that are connected to the power rails that we are trying to ascertain if there is a short. So since we cannot really find a reason why, from just looking why the CPUs, the section of the CPU was attempted, I guess that was done just to apply thermal paste. So now we're gonna basically put back the heatsink and then make basic voltage measurement. So I'm using a T5 again. It's not good. Just it's better to use a magnetic screwdriver. That way, your screws will not have to fly. And you can, as it is now, there's no power on the board, so it's fine. You don't have to worry about a screw dropping on the board. So it's totally fine. There's no cause for alarm. But once you introduce power into the board, then you have to be careful not to drop any metallic object on the board, so as not to breach any section of the board, thereby potentially causing enormous damage to the board. Because you never know where such a breach will occur, especially if it happens by the CPU line, or the PCH, which is basically on this machine, the same chip, PCH, and the CPU is embedded on one die. Okay, so now let's start with basic voltage measurements. Get a DC jack connected, and let's see what that's the state of the board. Let's see. First, we want to see what we get on our PPDCIN. So we want to see what we get on our PPDCIN. So we expect it to get 20 volt at each of the ports, and there are 4 ports on this machine. So we want a PPDCIN is expected to be 20 volt, and it's managed by CD2215. I'm just going to show you guys that. So that is. So we can measure that from one of the fuses, which is F300. So there you see it. We're supposed to get 20 volt. Now, 20 volt, that tells you that the CD3215 are fully functional. As regards to what the primary job, which is to get 20 volt. But then when they are not fully, when one of the CDs, because the 4 work as basically as one. When one of the CD3215 isn't working as it should, you most likely will get a 5 volt output instead of 20 volt. There will be no boosting taking place if one or more of the CD3215 is not functioning. So we check on this fuse to see if we get 20 volt. So that is 5 volt. Okay, so that's a good thing. Okay, yeah, that's a good thing because that's the start. So now that we get a 12, now that we're getting 5 volt instead of 20 volt, now let's see what we have on our PP bus. Let's see what we have on our PP bus. 12.32. That's fine. 12.32 basically tells us obviously that the board is not starting, and it also tells us that what we are getting at our PPDCIN, obviously it's not enough to give us. So let me put my multimeter here to make it easy for you guys. So here, now we get 12.3, yeah? and obviously the input is 5 volt. Now we want to check, so we want to check across all of the, first thing we want to do is we want to see if we can quickly pick up one or which of the CD3215 has failed, or if it's a failed CD3215, or if there is a required signal or power, because the 20 volts just doesn't make itself. There are required signals and power before the 20 volt can be made. So what we want to do now is we want to, first thing first, we want to just basically measure around the 4 CD3215s, the 4 that we have. I'm just gonna show you guys. So this is one. So for each individual port, it's being managed by a CD3215. So here, if I'm just gonna show you guys here, just gonna show you guys here. Sorry, bro. Hello, bro.
Yeah, I'm on.
Okay.
You know your.
Yeah.
Okay. I think that not push back. Again, around.
Okay, bring up now. Okay. I beg, no board. You don't get any board.
For.
Any board at all for parts.
No. I'll let that go check for this, but I don't get for now.
Okay, thank you. So if you so the CD3215s are identified using U3100. So this is one of the CD3215, and then on the other side of the on the right side of the board we have 2, 1, and 2, which is UB300 and then UB400. If we space bar to go to the other side of the board, we will have another CD3215 here, which is U3200, U3100, U3100, and U3200 is one side. UB is on the other side. So what we want to do is we want to see if we have 5 volt stable across all of the 4 ports. So if we will go into details of measurement, we'll go into details, which is basically to zoom into individual CD3215 to make sure that all of the requirements are present. Because if the signals required or the voltage required is not present for the CD3215 to be made, then for the 20 volt to be made, then it's going to be stuck on 5 volt. So first thing first, we want to see if we have stable 5 volt across all of the ports. What we want to do with that is one thing you want to look out for is when you measure your CD3215 input and then you get 5 volt that is not fluctuating at a particular port, then that tells you that it is fine. However, in a situation where you have, let's say you have 1 5 volt fluctuating on one port and then the other 4 ports, let's say you have the whole three ports are fluctuating, the 5 volt and then drop to 0 and then 5 volt, and what it tries to do is try to actually boost, which that tells you that the whole 3 ports are fine. The one port that's just going to stay without making any movement, without the voltage fluctuating, that is going to be the port where you have a faulty CD3215. So what you want to do now, so 2 things we want to quickly do. We want to quickly say, first thing first, we want to quickly measure across the 4 ports of CD3215 to be sure that we have 5 volt across all ports and that the 5 volt is also stable. So let's start with this one. Measure at this fuse, 5 volt. Let's just wait a little bit to see if it's stable or see if it's trying to okay, that's 5 volt is stable. Okay, let's move to the second port. Now we have to flip the board on that side to get the fuse. Let's see, 5 volt, is it stable? Yes, it's stable. Now let's check the other side of the board. There is also something we didn't do, which is because we are not the first to attempt this machine. That's why we didn't do that, which is to put the machine in DFU mode, to say if the machine goes into DFU mode. We didn't do that. I didn't have to do that because the state that I found the board was concerning, so I needed to be sure it was even something that is worth working on. So that's why we skipped that stage. 5 volt, okay, and it's stable. And then the next one, let's see, 5 volt to see if it's also stable. 5 volt and it's stable. Okay, 5 volt and it's stable. Okay, now we have to start to measure individual CD3215 to be sure that we have what's required. Now we're starting, by the orientation of the board, we're starting on the left hand side. Okay, we can just, let's start on the left hand side. Already can start on the left hand side, then orient the board the same way. orient the board the same way. Okay, so now this is where we are. Left hand side, our focus is going to be here, this and this, which is this two CD3215. So with the corresponding, so let's measure at the corresponding CD3215, which is going to be, so this port is going to be this one, while this is going to be no, this is going to be this, and this is going to be this. So this, we start with this. Now we want to check, when we click on this UB400, the power rails that we're expecting to have 1.8 volt. Let's see if 1.8 volt is present. That's one of the rails that we're expecting to have. So let's see if 1.8 volt is present. We measure that at CB408. Let's see, CB408. Yeah, okay. Okay. You can measure that at this cap. See if we have 1.8 volt present. 1.7, that's good enough. So that is present. And then the next one we want to check, we're not going to check everything. We just want to check. So that's an LDO. So now 1.8 volt. Yeah, let's see. That is also relevant. So if that is not present, then we will not have our 20 volts. So we're just only going to measure out the relevant signals and voltage. 1.7, not fluctuating. That's good enough. Okay. Now let's see. It's the next one is going to be PPDCIN. We already measured that. That is 5 volt. Let's see. Okay, the next thing we want to check. Okay, the I2C lines, yes, they are also important. Okay, these are important. Let's check that. Let's check. RB 3.3, that's it, that's fine. 3.3, and then let's check the 1.1 volt LDO PMC. Let's check that. Let's see, that's present. Another data lines, that's, we can measure that here. That's present. Now let's move a little down. Okay, 3.3, very important. Let's see, we can measure that at the cap. That is present. And the clock signal, clock 3.3. We can also measure that at measure that here, and that is present. Okay, that's good. And then let's move a little. Let's go down just a little bit. Pretty much that is what I'm gonna measure there. Now we're not gonna go further. Let's move on to the next CD3215. Let's see if we have same voltage. We just just measure. Like I said, we're not going to be measuring everything. We just want to focus on what's important. We've already established that this is present. Let's just check that again. Let's check that. We can measure that here, and that's present. Let's quickly move to the next one. This, we've established that it is present, so we don't have to check it again because that's universal across. So if it's present on one, it's going to be present on the other. And then this also we've established. Nothing to, yeah, let's check this. Let's check this. Okay, that's present also, so it's good. And the next thing we want to do is we want to see if okay, LDO, it's important, it's critical. Let's see if that is present. Yes, it's present. And then let's move as quickly as possible. we want to check what orders we want to check, what we want to check, what we want to check, what we want to check. What else do we want to check? We check the LDO. Let's check that. Let's check the clock voltage. See if it's present. Should be present because it's present on the other one, so that is also present. Now let's quickly move to the other side of the board. So I'm just gonna flip that, flip it like this to the other side of the board. So now we're working with that. So this port is going to correspond with this, and then this port is going to correspond with that. So yeah. So this is going to correspond with that. So we can just start with that one first, and then flip the board over, which is this one. Let's check if that is present real quick. Yeah, and then it's present. PPDCIN is present. We did check that. This is present. We did check that. It's present on one. It's going to be present on another. Next thing we want to check is we want to check if this is present. We can measure about here. And yes, it is present. Let's check check it there. Let's check this. Yeah, LDO signal. See if it's present. And yes, it is present. Clock. Let's check our clock. And that's present. I do have a strong feeling that this does not have anything to do with any of the CPD215, but yeah, let's just quickly follow this in part-time, check, put it on table present, clock present, that is also present. So at this point, we seem to, our CD3215 seem to be 100% okay. So what we want to do now is we want to do a random short check on the board, because yes, we are 7.5 volt. Now after the random short check is done, the next thing we want to do is we want to put the board in the shelf, and then try to put the machine into DFU mode and see if it puts into DFU mode. So right now we want to do a random short check on the board to see if we have any short, why the board has decided not to put into DFU. So we will be using capacitors to do our check, and we're using continuity mode because it's quick, and I don't have to look up all the time. All I just have to do is just listen to the beep. Once I get a beep, then I know there's an issue, and then I can check it out. I get a beep here. I'm just going to confirm what that cap is, see if it's supposed to beep. See if it's supposed to beep on both sides. Yes, it's supposed to be on both sides. Not just that it's on the CPU line and it has a low resistance to ground. So even though it beeps is 0.04416, so that's fine. It's not a short. Let's just continue. So we're just making a random check for sure. Okay, so we do not find any form of short or anything that stands out. So by the way we do the check for short. So we place one probe, black probe on ground. Your multimeter is in continuity mode, and whenever you see the sign here, so this is diode and that's a continuity mode. You set your multimeter. This points to this, basically it's your direction. Like it's now set to this, and then on your multimeter you find that sign as continuity mode. So when the black probe on ground, any of this can be your ground, any of this, yeah, screw hole can be ground, this ground, and then your red probe is basically now that's going to be your guide. So this is now where this is basically what you use for your drive to say that this basically points out or directs it, but the black has to be on ground. So then we have checked for short random at random, and then we don't seem to find any short. So the next thing we want to do is we want to put the board in the shell and check to see if it boots into DFU mode. So let's put the machine into DFU mode. We'll probably put in 1 or 2 screws to hold it in place. So for DFU we need power button. So not all this. No, we don't really need all the cables connected. But definitely the keyboard has to be connected, because we need the keyboard and the power button to put into DFU mode. Okay, so now we're to put all the screws together, all the cables. Okay. Yeah. I don't really have to connect. Okay. I don't really Okay. So I don't have to check everything, but I mean, I'm saying I don't have to connect all the cables. But I just put 1 or 2 screws. my keys. No, sweet. Maybe he wants to do something. He's my friend, so maybe he wants to take something inside the car. I'm just gonna get a cable for this 1 minute. Be back right now. This didn't have a battery data cable, so when you're when you're using your tweezer around the battery, be careful not to cause any type of breach. So be careful when you're using the tweezer around the battery. It's okay. Now we want to place this machine in DFU mode. The way we do that, we get a okay, so we get a cable to put this machine into. Also, you see, they made a mistake here. They long screwed them. They had to put it. The screws they put here was too long, and now the machine is actually been to. I don't know. Yeah. So to put the machine into DFU mode, two things we need. So we need a host, which is this is going to be our host. In our host, we need to have Apple Configurator. So we click on that. We open Apple Configurator, and then for Intel devices, we use the second port. For Intel devices, it's going to be the second port on the left. Is this my left? This is my left, yeah.
Yeah.
Okay, on the left. So the first, if this was an M1, it's going to be the first port. Well, I'm talking about putting the machine into DFU mode. But because it's an Intel device, we will be using the second port. So yeah, so this is going to be, so we plug it to that second port. And then we plug, now on the host machine, you don't have to worry. Whichever port you plug it on the host machine, it's fine. Obviously you have to get a USB-C cable. So whichever port you plug it in a host machine, that's not a problem, that's fine. Okay, and what do you know? The machine is actually in DFU mode. Okay, the machine is stuck in DFU mode. We didn't even have to put the machine in DFU mode. So the first thing that explains why it's stuck on 5 volt. So the machine is stuck in DFU mode. So what we want to do now, if it wasn't stuck in DFU mode, the way we would have put the machine in DFU mode was going to be Control, Alt, Shift, and Power. So basically Control, Alt, Shift, and Power is what, those are the combination keys we would have used to put the machine into DFU mode. But because it's already in DFU mode, we are not going to do that. So two options we have when the machine is into DFU mode. The first option is to revive. Now we want to revive. So revive, it's going to maintain the data of the client. So the data on the board is going to be saved. But then when we choose the option of restore, all of the data on the drive is going to be erased. So first we want to do is we want to revive. We want to choose the option of revive. So here there are two basic options that, we have the restore option, and then if we go to advanced, we have the revive option. So the first thing we want to do is we want to click on the revive option, because we obviously do not want to have anything to affect the client's data. So first we want to see if our revive option is going to work. I already have the file downloaded, so it's not going to download. If I didn't have the file, then it's first going to download and then install. But because the file is already downloaded, it's not gonna re-download. So it's just unzipping the file and basically install it now. So let's pray and hope that the process goes through. If it goes through, we should get an Apple logo. If it goes through, and then basically that will be it. We just hope that it goes through, and we hope we don't get any type of error. So usually when it's when you're reviving, sometimes when you revive it doesn't go through, you may have to restore. But then oftentimes if revive doesn't address the issue, restore will also not address the issue. So let us hope that Revive will address the issue, and yeah, and then this will be a done machine. Great, as you can see, that is our Apple logo, and then Revive fixed the option, and that is an amazing repair. So the reason why we didn't do this the first time was because the state we found the board was a little shocking, and was a little concerning, so we had to check to see why they had to do what they did. So that's why we had to take out the board to check if there has been any form of pre-work, and we found that yes, even though we did find a bit of a flux around the CPU MOSFET, but there was no actual component replacement on the board. So after we checked, we then checked around, we were stuck on 5 volt across all of the 4 ports. We checked to see why all of the CD3215 seemed to work just fine, so we didn't have issues with the CD3215, and none of it. And then we checked for short around the CD32s, and that also was not a problem. And then the next thing we had to do was to just do like a general short finding at random across the board, and also that also was fine. So after that is checked, the next thing we had to do was to do the first thing we would have done if we didn't find the board in that state. So for A1990, when you get these machines there, the first thing you want to do is you want to take out the back cover, check for short on the PB bus, because the A1990 are very common to have short on the PB bus, which is going to be caused by this particular component here. It's a capacitor on the that is supposed to that is attached to the buck converter, which is this buck converter for the NAND chip, which is your which is what is used for your SSD here. So so it's going to be this capacitor here, so C1980. So usually this capacitor go bad, and that usually happens through oxidation or a bit of dust in that section. So when it goes bad, what will then happen is it's going to create a short. So when that happens, you two things. Sometimes the capacitor itself just dies, and then the capacitor just needs to get out of the board, and then you have a fully functional machine. When it dies, it creates a short. So obviously when it creates a short, you have a short across the PP bus line, and that will kill the machine. So the first thing you want to do is you want to check for a short on these 2 fuses here. You want to check for a short here on your PP bus. Here you want to check for a short here. Your PP bus F701, and then F7000, F7001. You want to check for short. If you don't have a short here, the next thing you want to do is you want to see if the machine goes into DFU mode, which is what we would have done, but we didn't do that because obviously the state we found the board. So we're just going to wait for this to complete, and then our repair will be done. So we want this to complete, and we just hope that it completes successfully, and yeah, and then that will be the end of the repair. We're just waiting. We don't want this to be stuck. We want this to complete successful, and this is good. I mean, the fact that it starts is good. Okay, so we're expecting it to restart now. So that's the first. So we're expecting it to restart. Let's wait for it to restart. Let's wait for it to restart. Okay, same that we are restarted. We want it to restart. That's it. That's gonna be good. Let's keep waiting. Sometimes if it doesn't restart, we may have to force shut down and power the machine again. So T2 machines can be very tricky. Okay, that seems to be fine. It tells us there. So what we have at the back there. Okay, great. That tells us that the process was successful. So if we click on this, it's going to say that the machine is booted. And that is a good thing. There was no error. The machine was successfully revived. So what we want to do now is we want to shut the machine. Okay, fine. So now that's great. The machine is not starting because our battery is very flat. So we want to close it, leave it to charge for some time, and that's a complete repair. And that's it. Thank you. That's an A1990 complete repair, and we are good.